Hey, this is Mr. Warden. This is the video do now key for do now 24.1. And here we have an image of a hydrogen atom. It's not an actual photo. It's the result of pinging a hydrogen atom with a lot of electrons and figuring out roughly where some of the pieces of it are. I'm not even sure if it's electrons, but it's not a formal photograph because hydrogen atoms are smaller than the wavelength of visible light, but it is what an approximation of a hydrogen atom really looks like. Those are kind of where the electron is buzzing around. There's only a single one, but it's just moving around so much that it's all over the place. And in the middle is the tiny, tiny nucleus where most of the mass is. However, 73% of the mass of the sun is hydrogen. And that comes to about 1.45 times 10 to the 30th kilograms. So if a single hydrogen atom has a mass of 1.67 times 10 to the negative 27th kilograms, how many hydrogen atoms are there in the sun? Well, if we want to know how many pieces there are, then we're looking at division. So we're going to divide 1.45 times 10 to the 30th by 1.67 times 10 to the negative 27. So let's organize that. Let's actually get that information. So it's 1.45. So first thing we're going to do is we're going to group it 1.45 and divided by 1.67. So we're going to group the coefficients. And then over here, we'll group the powers. 10 to the 30th divided by 10 to the negative 27th. And now I'm going to work out what's 1.45 divided by 1.67. I'm going to cheat and use the Google calculator real quick so I can get the answer really quickly. So we get 0.8682. I'm going to round that to 0.86 for right now. Okay, so we're going to get 0.868. See, that's that what I got? Yeah, 0.868. And then over here, we're going to be times 10 to the 30 minus negative 27 power, which is going to be 10 to the 57th power. So it's going to be 0.868 times 10 to the 57th power. We got to make 0.868 10 times bigger, so it'll be 8.68 times 10 to the, we got to make that 10 times smaller, so 10 to the 56 hydrogen atoms on the sun. Approximately. This is rounded, of course. Okay, now the Earth has a mass of 5.94 times 10 to the 24th kilograms, and the sun has the mass of 1.9885. Hang on, did I get a bad number up there? Yes, no, I did not, because that was 73%. Never mind, I thought I tricked myself, but I tricked myself tricking myself, so I was right. So the sun has a mass of about 1.9885 times 10 to the 30th kilograms. So the Earth has a mass of 5.94 times 10 to the 24th kilograms. How many times more massive is the sun than the Earth? When you're trying to figure out how many times more something is, you're dealing with division. So we're going to deal with the sun's mass, which was 1.9885. So we're going to group our coefficients. So 1.9885, and we'll divide that by the Earth's mass, which was, and we'll deal with the 5.94. So that's the coefficient for the Earth, 5.94. And then we will group the powers. The sun was, the power was 10 to the 30th, and the Earth, the power was 10 to the 24th. And it's all, okay, they're both kilograms, so kilograms will cancel out. So we just want to know the ratio here. So let's work out what is 1.9885 divided by 5.94. I'm going to cheat and use the internet again, and I get 0.33. I'm going to round that to 5, so 0.335. So that becomes 0.335, and that's going to be times 10 to the 30 minus 24, which is going to be 10 to the, so 30 minus 24, just go ahead and leave that there, times 10 to the 6th. And then I can make that scientific notation by making 0.335 3.35. It's 10 times bigger, so 10 to the 6 has to be 10 times smaller. Okay, so the sun is, I'm going to use the word not bigger because that's a little ambiguous. I'm going to say more massive. Okay, now a light travels at about 3 times 10 to the 8th meters per second, and there are about 3.154 times 10 to the 7th seconds in a year. Now, given that distance equals speed times time, and a light year is how far light travels in a year, how many meters is it to Alpha Centauri, which is 4.3 light years? So what we need to do is figure out how many meters there are in 1 light year, which is going to be the speed times the time. So I'm going to do 3 times 10 to the 8th times 3.154 times 10 to the 7th, and multiply that times 4.3. So let's put all that down here. I'm going to gather, this is the one that I don't have memorized. So I'm going to just grab that. Okay, so we've got 3 times 10 to the 8th times this times 4.3, which we could call times 10 to the 0 if we wanted. So I'm not going to really worry about 10 to the 0 because that's just 1. But I'm going to treat 4.3 as one of the coefficients when I group things. So I'm going to say 3 times 3.154 times 4.3. That'll be one grouping, and then I'll group 10 to the 8th times 10 to the 7th. Okay, so I'll cheat and use the Google thing and get the calculation for the coefficients. Nothing wrong with doing that, y'all. And I get 40.6866. So I'm going to round that to 40.6866. I'm going to round that to 40.69. All right. And you could make some different choices about where you round it, but that's where I'm going to round it. And then over here, I'm going to be doing 10 to the 8 plus 7. And then I'll simplify that. So 40.69 times 10 to the 15th, since 8 plus 7 is 15. And now I've got to make 40.69 10 times smaller, so 4.069 times 10 to the, this has got to be 10 times bigger since I made the other one smaller, times 10 to the 16th meters. Okay, to, is it Alpha Centauri or Proxima Centauri? They're about the same. We're using Alpha Centauri. I mean, they're not really that close to each other, but compared to where we are, they're pretty close. Okay, so that is how far it is in meters to Alpha Centauri. That is a long walk. All right, I'm going to stop the video, and I hope that was helpful.